So I had hoped to have the answer to this question by the time I came here. I still don't, so I'm looking for suggestions. I just asked Yusuf if ChatGPT-4 could answer it. And I think it's still a little bit beyond ChatGPT-4. Let A be an n by n matrix, and let lambda be a simple eigenvalue of A. So let x and y be the unit left and right and left eigenvectors. Then we can write the spectral decomposition. Whoops. No. We can write. Okay. We can write the spectral decomposition of A in the following form. Yeah. Okay. Finally. Lambda minus z inverse xy star over y star x. That's the projection onto the eigenspace, the eigenvector associated with eigenvalue lambda. And then there will be projectors onto the other eigenspaces. And if there are Jordan blocks, there will be some nilpotent matrices in here as well. But the important thing is, if z is much, much closer to lambda than it is to any of the other eigenvalues, then this term will certainly dominate. And in that case, A minus Zi inverse, the resolvent, will be approximately equal to the rank 1 matrix lambda minus Z inverse xy star over y star x. The condition number of a simple eigenvalue lambda is defined as 1 over the inner product of the left and right eigenvectors, the absolute value of that. This provides a measure of the amount by which lambda changes when A is changed by a small amount. And we say that A is ill-conditioned if this number is large, that is, if y is almost orthogonal to x. When x and y are nearly orthogonal, well, if x and y were truly, keep doing that. If x and y were truly orthogonal, sorry, forward. If x and y were truly orthogonal, the numerical range of the matrix xy star, that matrix would be unitarily similar to a 2 by 2 Jordan block followed by zeros. And the numerical range would just be a disk of radius 1/2 about the origin. When they're almost orthogonal, that's almost the case. That is, the numerical range, or the field of values, which we heard about before, of xy star is close to a disk of radius 1/2, about not exactly the origin, but a point very close to the origin, 1/2 y star x. So when z is very close to an ill-conditioned eigenvalue lambda, the resolvent looks like a rank 1 matrix, and its numerical range is approximately a disk, about a point very close to the origin. That's one case in which the resolvent looks like a rank 1 matrix. However, what I found is that the resolvent may look like a rank 1 matrix for a much wider range of z values. This is the Gercher matrix that we heard so much about earlier. And what this picture shows is that everywhere inside this region, the ratio of the second largest to the largest singular value of A minus Zi inverse is, is less than or equal to 10 to the minus 3. Now, that's not at all what I would have guessed. I would have guessed that maybe it would be less than or equal to 10 to the minus 3, maybe on some disks of radius 10 to the minus 3 about the eigenvalues. But this is a much larger region than that, where the resolvent really is very close to a rank 1 matrix. It's not the xy star that we saw before. There's no close eigenvalue, but it is close to the rank 1 matrix, sigma 1, u1, v1 star, where sigma 1 is the largest singular value of the resolvent, and u1 and v1 are the corresponding left and right singular vectors. And indeed, they are almost orthogonal to each other. They're orthogonal to within 0.001 on a region that is almost a little bit smaller than this one. Okay, so the resolvent looks like a rank 1 matrix, at least for the Gercher matrix, over a pretty large region. And as I mentioned, since u1 star v1 is almost 0, it means that the numerical range, if I take a point z on the boundary, I took a point on the boundary of the, where sigma 2 over sigma 1 was 0.001. If I take a point there, u1 star v1 is maybe a little larger than 0.001, but what this says is that the numerical range will not be very exciting. It will look like a disk about the origin, and it does. Okay, well, why was I interested in this? First of all, it could be very interesting in applications if you're working with a very large matrix and you need to work with the resolvent. If you can approximate it well enough by a rank 1 or a low rank matrix, that's a huge savings in time and storage. The reason I became interested in this was I was interested in estimates of the norm of a function of A, norm f of A, based on the maximum value of f on various regions in the complex plane. And one simple way to get a bound on norm f of A is to use the Cauchy integral formula, take norms on both sides, and replace the norm of the integral by the integral of the norm. Okay? That gives you an upper bound on norm f of A. It's less than or equal to 1 over 2 pi I times the integral over the boundary of this region omega of the norm of the resolvent, and then times the maximum value of f on the region omega. Okay, well, recently, Michel Crouzet and I proved a result where we essentially, there were various aspects to this result. It was a little bit complicated, and I won't talk about some of the geometrical things, but we essentially were able to replace the norm of A minus zi inverse in this integral by the integral of the absolute value of a certain point on the boundary of the numerical range of the resolvent. And does this lead to a sharper estimate of norm f of A? Well, it depends on what omega is. For certain sets, it certainly does. If omega is the numerical range of A, then the answer is yes. This reproduces the Crouzet-Palencia result, 1 plus root 2. And Crouzet was also able to show that if we took a disk about a point C of radius 1 over, well, the numerical radius of A minus Ci inverse, so the resolvent comes in again, that was a 3 plus 2 root 3 spectral set. So I thought, well, let's try some smaller regions. The field of values or numerical range can be a rather large region. Let's try some smaller ones, like maybe the epsilon pseudospectrum for some fairly small value of epsilon, 10 to the minus 3, say. Do we get a better result than the result from pseudospectra, where the epsilon pseudospectrum is the set where the norm of A minus Zi inverse on the boundary is equal to epsilon inverse. So then this integral just becomes the length of the boundary curve over 2 pi epsilon times the norm of f on the pseudospectrum. Well, the answer is no, I did not get better results. Okay? If the boundary of omega comes even fairly close to ill-conditioned eigenvalues, The results were pretty similar to what I would get by using the norm of the resolvent in here rather than this point, rather than integrating this point on the boundary of the numerical range. So why is that? Well, it's because the numerical range of the resolvent looks like a disk, which means a disk about the origin, more importantly, which means that every point on the boundary, whichever one it is that we integrate, has magnitude equal to the numerical radius, which is within a factor of 2 of the norm. So while this bound that replaces the norm by the integral of a certain point on the boundary of the numerical range of the resolvent leads to much smaller estimates of norm f of a on fairly large sets like the numerical range, on these smaller regions, it does not. So I wanted to understand why, and as I mentioned, it's because the numerical range of the resolvent looks like a disk about the origin. Now, this is definitely a phenomenon that has to do with ill-conditioned eigenvalues. If I put in a normal matrix, say a diagonal matrix, with the same eigenvalues as the Gercher matrix, you won't see this. None of the contours that I plotted previously even show up on this plot. I ended up plotting the contour where the ratio of the second largest to the largest singular value was 0.5. And it's a small, a small region there. So this is definitely a phenomenon associated with ill-conditioned eigenvalues. And it's not a phenomenon that works only for the Gercher matrix. This is another interesting matrix with ill-conditioned eigenvalues. It's called the transient demo matrix. And well, what you can see is that in this annular region, the ratio of the second largest to the largest singular value of the resolvent everywhere in here is less than or equal to 10 to the minus 3. And likewise, the left and right singular vectors associated with that largest singular value are almost orthogonal. Their inner product is less than 0.001 in a slightly smaller annulus. Now, both of these are Toeplitz matrices, so you might think, well, this has something to do with Toeplitz properties, but in fact, it holds even for matrices that are not Toeplitz. This is another one from the matrix gallery in MATLAB. It's called the sampling matrix. It has integer eigenvalues that are ill-conditioned, and again, there's a very large region where the resolvent, A minus Zi inverse, is very close to a rank 1 matrix, and where the U1 star V1, U1 and V1 are almost orthogonal to each other. And, well, those are the matrices I'm showing, but if you go into MATLAB and go to the matrix gallery and try any of the ones with ill-conditioned eigenvalues, you will see this same phenomenon. So the question then is why? Well, to try and understand why, first, let's work with the smallest singular value of A minus Zi instead of the largest singular value of A minus Zi inverse. The ratio of the smallest to the second smallest singular, or the smallest to the second smallest singular value of A minus Zi is the same as the ratio of the second largest to the largest singular value of A minus Zi inverse, because the singular values are just inverses of each other. They have, the right and left singular vectors, I guess, are shifted or switched. Let's start where we know something about these singular vectors. Let's start by taking a simple ill-conditioned eigenvalue lambda And let's start with A0 equal to A minus lambda I. That has a 0 eigenvalue now, okay? And that's also a 0 singular value of A minus lambda I. And the associated eigenvectors, if lambda is ill-conditioned, they're almost orthogonal to each other. And the associated singular vectors are the same as the eigenvectors. So we start at a place where A has a 0 singular value, and the A minus lambda I has a 0 singular value. And the corresponding left and right singular vectors are orthogonal, or almost orthogonal to each other. And then we're going to perturb A. We're going to replace this A0 by A0 minus Zi. Now, there are many bounds on the change in singular values or vectors due to a small perturbation to A0. I listed one classic reference, Stewart and Son, but there are many others. But they deal with general perturbations and really are not strong enough to explain these observed results. Our perturbation, minus Zi, is particularly simple, so hopefully we can say a little bit more than in the general case. Well, let's start with the following theorem. So let lambda be a simple eigenvalue of A, and consider the matrix A0 equal A minus lambda I, write its singular value decomposition. The smallest singular value of A0 minus Zi, so now I'm going to perturb it a little, is less than or equal to the absolute value of Z times the absolute value of the inner product of the singular vectors that correspond to that 0 singular value, plus a term involving the absolute value of Z squared divided by the first non-zero singular value. Okay? So what this says is that if un star vn is very small, then this 0 singular value won't grow like Z, it will grow more like Z squared. Okay? And the way to prove that is simply to find a vector that you can apply A0 minus Z to and get something with much smaller norm. And I should mention I'm always talking about the 2 norm here. Okay, so what happens, I chose this vector. When I apply A0 to Vn, I get 0, un times sigma n, and sigma n is 0. When I apply A0 to columns 1 through n minus 1 of V, I get u n minus 1 times sigma n minus 1. So what I get when I apply A0 to this second term is just un minus 1 star times Vn. And now I subtract Vn from that. That's the coefficient of Z. And then I've got this Z squared term. The first term, that's just un star Vn. And so its norm, it's multiplied by Z, its norm is the absolute value of Z times un star Vn. And the second has norm at most, well, Z squared times 1 over the first, the second smallest singular value of A minus Zi, the first non-zero one. So assuming that that one is not too small, this says that sigma n will not change like Z, but more like Z squared when un star Vn is almost 0. What about this ratio? That determines sort of the factor of A minus Zi, or A minus Zi inverse, that is like a rank 1 matrix. Well, we can be a little sloppier here if we like. What happens, let's assume that sigma n minus 1, that first non-zero singular value, is not tiny. It's, say, on the order of 1. Then over a small distance Z, what happens? Sigma n minus 1 may grow, but it could possibly decrease to what it was before, minus the absolute value of Z. It won't decrease any more than that because singular values are well conditioned. And so the ratio sigma n over sigma n minus 1 of A minus Zi, which remember is the same as the ratio sigma 2 over sigma 1 of A minus Zi inverse, will become this. If, say, this is 10 to the minus 5, the absolute value of Z is 0.1, then we get 0.01, and then sigma n minus 1 just moves from 1 to 0.9, and basically this is like 0.01 squared, like Z squared. How tight is this bound? Well, the answer is not very tight at all. This is the Gertner matrix again, and what the bound indicates is that sigma 2 over sigma 1 will be less than 0.01 everywhere in these blue circles. The circles have radius larger than 0.01. In fact, it's like 0.1 because it's the square now of Z that determines the change in the singular values. But it comes nowhere near explaining this very large region where, in fact, sigma 2 over sigma 1 is less than 0.01. Okay, well, another approach to trying to understand this is differentiation of singular values and singular vectors. Now, in general, the SVD is not continuously differentiable unless you allow singular values to become negative. There are some nice works about this back from the 1990s. However, if we differentiate, just do directional derivatives, at least provided we do not encounter matrices with multiple singular values, we can differentiate the singular values. So if we fix an angle theta, set Z equal to R e to the I theta, and we can determine the derivative of sigma with respect to R for each given theta. How does this work? Well, it works very easily. You just write down the equation for the singular value decomposition, and then you differentiate term by term. You use the fact that U star U and V star V are the identity. This means that U star prime times U plus U star times U prime is going to be 0, and similarly for V. And, well, this could be written as U prime star. So this is just the conjugate, the Hermitian transpose of this. So what this says is that U star U prime and V star V prime are skew symmetric, skew Hermitian. So if we take this first equation, multiply on the left by U star and on the right by V, we get an equation for sigma prime. We use the fact that the real part of the diagonal entries of U star U prime and V star V prime are 0 because of this skew Hermitian property. Okay. And so we obtain an equation for sigma prime. It's the real part of the diagonal of U star A prime times V. For us, A prime is very simple. It's just minus e to the I theta times the identity. And so sigma n prime, the rate at which this smallest singular value of A minus Zi changes, is minus the real part of e to the I theta times un star Vn. We know that at the start, sigma n is 0, un star Vn is tiny, so this tells me that at least initially, sigma n is going to change very slowly as I increase r in this r e to the I theta addition. Okay. So That's what I just said. At least initially, sigma n is going to change from 0 very slowly. I should point out that when we do have to be a little careful when we start, when r is 0, sigma n prime, I want it to stay positive or non-negative. So when sigma n is 0, we have some extra choice in choosing un. Usually once vn is set, un is determined because a times vn is un times sigma n. But if sigma n is 0, I can multiply un by an arbitrary unit scalar, and I'll choose that unit scalar so that this comes out, sigma n prime comes out to be positive or non-negative. Okay? Okay. So, as I mentioned, the slow change in sigma n holds as long as un and vn are almost orthogonal to each other, and sigma n is still small. Okay. So how do we show that un and vn start out almost orthogonal to each other? Do they stay almost orthogonal to each other? Well, again, we can differentiate the inner product, un star vn. And when we do that, we get this expression. This term is small as long as sigma n is small. This one looks a little scary because we're dividing by sigma n, but we've chosen un when sigma n is 0 in such a way that the imaginary part of this is 0. And in fact, in the limit as you approach 0, this term goes to 0. But there's no reason offhand to believe that this term will be small. It is in the numerical experiments that I've done, and I've done a lot of them, all of the matrices in MATLAB's gallery, many from the book by Trefethen and Embry on pseudospectra. And they've all had this sort of property if they had ill-conditioned eigenvalues, and un star vn was almost 0. But I can't prove that. Okay? So it's not obvious from differentiating that un star vn remains small. It does in the test problems, but that means they must have some other special properties that I haven't taken into account. So what have we taken into account? How's my time? All right, let's quickly say what have we taken into account, and then I will stop. If lambda is an ill-conditioned, we're assuming lambda is an ill-conditioned simple eigenvalue of a, so that a minus lambda I has a 0 singular value with nearly orthogonal right and left singular vectors. This implies, at least initially, that sigma n changes very slowly. We've assumed that sigma n minus 1 is not tiny, otherwise those could cross when they start changing. So that for small r, this ratio remains small. We surely must at least have the assumption that un star vn, the derivative of un star vn, evaluated at r equals 0 is small if we expect this to remain small for a wide range of r values. And again, this is the case in all of the test problems that I've tried. I'm not sure sort of what this corresponds to in terms of the matrix A. And I'm also not sure if this added assumption is sufficient. So I think I'm out of time, so I will stop there. Thank you.